Okay, recording has started. So let me share my screen. I hope it is visible to everybody.
Yes, sir.
Yes.
Okay, great. So I continue from where I left in the last class. Let me go to the presentation mode. Yeah. Okay, so in the last class we have seen that how we can break your total, I would say, programming project into multiple files, more precisely multiple header files, multiple C files, and eventually you compile your final application with a main function alongside the individual object files. Okay. But the problem with this approach is that it's not a problematic thing anyway. The problem is that you are always thinking about a main function, a final product. But we will not necessarily think immediately about the final product, that is programs with main functions. Okay. For example, we think about the math library. Okay. Somebody must have written this square root, pow, tan, right? And they are not meant for immediate use. So they will keep those bundle of so-called object codes into something so that any user later can link or include those definitions and also the implementations in their codes. Okay, without worrying too much about how they are implemented. Okay, so library is exactly like that. Okay, so you precompile a set of files without a main function, and eventually compile those object files into a so-called archive. Okay, so it's something like this. A library is a precompiled archive of object files. So these are executable codes. Now, I would not say executable codes, but some machine codes of individual functions which are not immediately linked to any program with main. Later, if you want, you can include these object files or the archive and use the functions written. Okay, so this is, yeah, so this can be linked to user codes during compilation if it is so-called static archive, or during runtime if it is a shared or dynamic archive. Okay, so now if I, for example, look at the math library, it consists of several components. First, there are several header files, okay, which define the data types like float, double, and so on. It also has a collection of function prototype definitions, power, square root, arctan, cos, hyperbolic, and so on. The math library also defines several constants like pi, e, log 2e, square root 2, things like that. And finally, you should have a pre-compiled archive of all the implementations of these functions like pow, square root, etan, and so on. Okay. Now, when you write a code, you need to do two things. First, you have to include math.h so that during compilation or the first stages of compilation, the compiler precisely knows what is your float data type, what is your double data type, what is the constants like math pi, math e, math log 2e, these things, how they are defined. And also, by doing so, you are instructing the compiler, for the moment the preprocessor to be precise, more precise, how these functions look like, what they take as input and what they produce as output. Okay. For the immediate compilation of your code, you need only these three things: the data types, function prototypes and the constants. Okay. In the last stage, which is called linking, okay, now there are two types of linking as I mentioned in the last class. It may be a last stage of compilation, that type of linking, or it may even be a runtime linking. Okay. Then that is the stage where you actually require the implementations of the math functions, the exact bodies in the language of the machine, target machine. Okay. So this precompiled math library is needed. This is the item 4, only for linking to your final executable. And that linking may be static or dynamic. Okay. And you specify the option -lm for the compiler to know that you are asking for the linking to these external functions. The definitions are external. Okay. It is not part of your code. Okay. So that's what a library essentially stands for. A set of header files defining the first 3 items and one archive, precompiled archive containing the actual implementation of the functions. Okay. So we will now see how you can yourself prepare some such libraries. First of all, as I mentioned, there are two types of libraries, static and dynamic. Dynamic libraries are usually called shared libraries in Linux terminology. So these libraries have some, I would say, naming convention. The math library has name M. Okay. M is just the name of the library. But whenever this M library is sitting somewhere, it has a prefix of lib and a suffix or extension of .a. So the math library has the name libm.a. Okay. So this is a standard convention. Lib followed by the library name, then .a. This is a static library. And functions from static libraries are inserted in your code, in the executable code, during the last stage of compilation. Okay. Whereas if I talk about shared or dynamic libraries, they also have the same naming convention. Prefix is lib, only the extension is something called .so. SO stands for shared object, and it may be followed by a version number, like .so.1, .so.2.0.4, something like that. Okay. But for simplicity, for the moment, we will restrict our attention only to just lib.so kind of stuff. So the math library, if it is present in the static, in the dynamic form or shared form, it will have the name libm.so. Okay. And these functions that are defined in libm.so, they are not linked during the last stage of the compilation process, which is done by LD. Okay. Instead, when you run your a.out or whatever application, then this libm.so will be loaded to the memory, and the definitions of the functions, or I would say the implementations of the function that you use in your a.out will be read from this copy of libm.so in your memory. Okay. So function from shared libraries are not inserted in the executable, but they are read from the .so objects during runtime. Okay, so that's the difference between static and dynamic or shared libraries. And a good thing about dynamic libraries is that here, if you look at this static libraries, the entire static library is usually included in your executable. That adds to the size of the executable file. Whereas .so files, they are not attached to your executable, and multiple programs, multiple processes using objects or using functions from the shared objects can read from this copy. So that usually makes much smaller code. Okay. So to start with, today we will see how we can ourselves build static and dynamic libraries. Okay, any question at this point?
Sir, then why don't we, sir, why don't we make all the libraries, means we use them as shared or dynamic libraries, because it has these advantages.
What is the question?
Sir, I'm asking that the shared libraries have the advantage that they are not inserted in the executable and etc. So we should use only those libraries. Is there a place
Okay.
where we use static libraries?
Okay, so there are several issues here. For example, if you insert the I would say functions in the static fashion, then your code is a self-sufficient code. You do not have any runtime dependency. Okay. So you move to another machine, this, I would say, your executable will run. So on the one hand, this is in some sense more, I would say, comfortable because this gives more self-sufficient or independent codes. But if you want to run an executable which requires a shared object, this object has to be there in the target machine. So if you compile your code with the shared object and try to run it on another machine, if that is not present, your code will not run. Okay, each has its own advantage or disadvantage, but these are two standard ways of doing it. So does that answer your question?
Yes, sir.
Okay.
There is another issue. So if it is not there, okay, you will at least get an error. Okay. The other problem happens, okay, is if you have compiled with a shared library, okay. So what happens is when you compile with the shared library, some reference to the codes in the shared library gets made. So when the shared library is there in the runtime, those references tell you where to look in the shared library to do that. So the other bad problem that happens if the shared library version changes. So your code now says that this function is actually the third function in the shared library. But when you run it, by that time, somebody has recreated the shared library, inserted some more function. So that function has actually become the fifth function. Okay. So I'm talking in a little bit high level. Okay. It's not exactly like that, but the idea is exactly the thing. So then you may unwittingly actually link when you actually run the program, it finds the library. Okay. But then you link with basically a wrong function or wrong version of the function. So it is the same function, but then something else changed. So one is as if that it is not self-sufficient, so it has to be there. The other problem is a version mismatch can happen if you're not careful. I don't know, but some of you, at least I remember in the first year, first semester labs, at least in my section, had this problem with code blocks giving you strange errors. So there's basically a version mismatch. With the DLLs that, so there are lots of shared libraries in Windows. Those files are .dll files. And then every program that runs on Windows depends on some of those DLLs. But then there has to be a version match correspondingly. So if you have called a function, for example, which is not yet there because your version is earlier and the old DLL is earlier, then the function that you called in your code, it still finds the complete DLL. The name is the same, but the function that you have written in your code is not there in there. So if you do not have the DLL, so the shared library, not DLL, the shared library in general, then you will get an error while running the program itself. But if you have a shared library, but with wrong versions, these mismatches and so on, you will get very strange errors which are very tough to debug actually. So it depends on your need. If the size is not too large, you go with static, or you want to carry it over, you know that you will need to run it on something where the DLL may not be there, the shared library may not be there. But if you are very sure the shared library will be there, then you probably will not do static. Ready, I'm done.
Sir,
Yeah.
like the static libraries means they contain functions which do not like depend on the architecture of the machine. Is that
No,
so?
no, 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 no. That's a whole different question. You cannot compile something for, let's say, your Intel architecture and take it to a IBM PowerPC architecture. Because ultimately, your runnable code, okay, is the machine language, just very simple views of machine language instruction that you are telling the CPU to run. So each CPU understands a different set of instructions, each type of CPU architecture. So if you take it from, let's say, in just one second, if you take it from an Intel architecture and go to a PowerPC, you have to get the source code, run it again. Sorry, compile it again.
Yeah,
But
but
you may
like my question is the static libraries, why are they exactly there? Like, what is the main purpose? Like, why are they static?
No, but you may want to take it from you compiled in Linux in your PC here. Okay. You may want to take that piece of code, executable, and run it on another Linux, same kind of PC. But the shared library may not be there. It may be there, it may not be there. Depends on the application. Then the code will run, same architecture, everything same. Okay. But then when it tries to run, it won't find the shared library.
Sir, what if the static library is not present? We only share the code.
No, static library. What is the?
So like we only share the code.
Once you have the executable, you don't need the static library anymore. That is why the size increases. See, when this you do -lm, you have that libm.a. Okay, you do that only during compile time. Once you have compiled for a static library, all the code that you need is in that a.out. That is why the size goes up, because the entire static library's code comes into this. So you don't need the library after you have created the executable. It's already linked. You can just go run the executable on the same architecture, same operating system, and so on. But shared library is that when you compile, when you link, it does not actually add the code. It just makes reference to that shared library. When it runs it, it looks for that shared library and then it uses those reference to go to the appropriate parts of the library. Does that make it any clearer?
Sure. So for case of static library, suppose like in case of math library, I just want the square root function, but still like the entire
exactly. Exactly. That's the bad thing.
Okay.
That is why the entire thing is done. Has to be at all the entire library will get added.
Okay, sir. And like, sir, I had one more doubt. Like, could you scroll to the previous slide?
Previous slide. Yeah.
Yes, sir. So like here for a library, it's written like it consists of some like .h files containing all the data types and then the functional prototypes, right? And plus there would be a like a implementation file like a .c file. So like from this part, I like understood that a library would be a collection of some .c and .h files. But like in the next slide, I saw the
source files. Somebody precompiles this, and this precompiled mainless version will be clapped together in the form of a library. Okay, .c files are no longer there.
So I think the line is a little bit, means you should read properly. So the library is also code. So for that code, every code comes from some source files, .h, .c, and all those things. Only thing that you have compiled that, kind of put in the bundle. So now the library what we are talking about is actually the compiled code. Okay. When we say math library consists of the following, basically what do you need to create the library? You need the .h file, .x files, all those things. Okay. But then you compile, which is what Eddie is going to show you today. And the final product that you get is the actual library.
Okay, so like
So
after
libm.a is the library, it's the compiled code. But libm.a, the implementation of it, you don't have to do it, it's not given to you, but there will be some source codes containing the functions for square root. Somebody has to write the function for square root, right?
yeah.
You don't write it because it's so many people use it that somebody has written it, compile it and say, no, now you don't worry about the source code, what header files, what source code, something. You just got this library, you just use it.
Okay, so like essentially after compilation of these .c and h files, we get the resultant .a or .s file. Like,
Yes.
is it correct?
Yes, that's what Eddie is going to show you.
I will demonstrate you how to do
Okay.
Exactly.
Okay, so thanks.
So you don't want a the executable file with the main function or everything, but you want something that somebody can tag on with their main function, call the functions and so on. Just wait for a few slides. I think it will become clear.
Okay.
Sir, I have a doubt.
Yeah, tell.
Sir, but it's not related to C. Can I ask? It is related to library, but not C.
Go ahead, ask anyway. Let's see.
Sir, in a few other languages, we have this concept of importing some parts of the library. If there is the math, suppose that there is some math library, so math dot something. So, sir, is that any efficient from than this?
No. Import is same as a hash include.
Yes, sir. So in that we have some parts of, we can import the
Hash
parts
include
of some
import,
library
there is
instead
not
of the
much
whole.
difference. Some languages, what they do after compilation, like Java, it does not produce machine dependent code. Sometimes they produce what is called machine independent bytecodes. And these bytecodes are perfectly, I would say, portable. From one machine to another, you can port, but there should be some machine specific, architecture specific runtime environment that converts those bytecodes to the actual executables and run it. C does not do it that way.
Kind of dependence is similar
C
to
does not do it that way.
Okay.
That is true. C does not do it that way. That is for certain. Okay.
So those languages is kind of for interpreted languages basically. Anyway, let's go back to C.
Yeah. So these are slightly different ways of doing the same thing, but anyway, C does not do it. So keep it in mind. Otherwise, import is basically same as hash include. Okay, you are not actually importing, I would say, the function bodies. Okay.
Sir, can a program or like an executable edit a library?
Once it is precompiled, how are you going to change it?
You change only the source files.
Okay.
But there is a thing. There are calls to add something to the library or delete something to the library. We will not go do this in this class. You can do that, but you cannot say that I want to, change the code of the square root like this, just this one line I want to change or anything like that. So right now at the beginning, because we are learning it for the first time, keep it simple. Plain compiled language, you will create the library once from the source and headers, and then you will use it. Okay, understand this, but there are calls, I think I will find out. It's calls to add functions or delete functions from the library. From shared libraries, from static libraries, I do not think so. From shared libraries.
Okay.
Yeah. Okay. Okay. So let us now understand the technology, how I can myself create .a and .so files. So I'll start with static libraries. So you recall that I have written the utility functions, defined them here, also with some type defs, stack, queue, node pointer. Okay. And I implemented those things in stack.c and queue.c. Now, my stack.c and queue.c are mainless functions. So what I can do, I can club together all the function definitions, the bodies, in the form of a library. Later, any application program, it is not necessarily that, okay, so I want to build the static library and its name will be staqueue. Since it's a static library, it starts with lib and its extension is .a. And this will contain all the stack and queue functions, implementations of this, but in compiled machine specific format. Okay. Later, okay, so for example, okay, this is also important. There should not be any main function because main functions will be written in the application codes. So application programs, as we have seen, something like stackcheck.c, that will contain the main functions. But what this main function, I mean, this application program will do is that it will call the predefined functions that are just clubbed together here. Okay, you don't need no longer to, once this is prepared, you do no longer need to look at how this push, pop, enqueue, dequeue, init, queue, and all these things are defined. You should know their input-output behavior only. Okay. So the two basic ingredients of building this lib stack is first, compile individual source files with the -c option. Okay, this we have already seen. For example, if I compile the stack.c with the -c option, it will generate stack.o. This one will generate q.o. Okay, this is just a compilation of some functions. And then I club together this individual .o files using a command called AR, which is an abbreviation of archive. Okay, so combine the object files into a single archive. In this case, it is going to have this name using the command AR. Okay, so let us see how we can do it. Yeah, so first of all, gcc -c stack.c. And it's always a good practice to run it with -w all or maybe -w itself. So this will generate stack.o. Then you compile q.c with the -c option. It will generate q.o. Eventually, you prepare this archive. So RCS is a set of directives. So you look at the man page of AR to understand what exactly R is, what exactly C is, what exactly S is. If you do not fully understand, don't worry. For the moment, it's sufficient that you can just follow this way of doing it without much understanding. But if you are interested, you should look at the man page of AR. So you just say MAN space AR. Okay, and you see what R means, what C means, and what S means. Then you give the name of the file, the archive that you want to build, then stack.o, q.o, the individual object files, one after another. Okay. Once you do that, if you want to have a directory listing, you will see that this is there, and they are combined together in the form of this library. Okay.
Sir?
Yeah.
Sir, if we look at the size of this .o, both of the .os, they are a bit less, their sum is a bit less than the libstack.a. Why is that?
Because you look at this AS. This static library has what is called a symbol table. So it will be slightly more than the sum of this and this. So that symbol table is one thing that should be included in this libstack.a file. So that is one of the reasons why this size is bigger than this plus this. Okay.
Also, so it's a good question, but do not try to read into too much into the sizes. But the format is not just these two .os get stuck together and some small symbol table gets made and that's the library. There is an internal format, the format changes. Okay. So little bit of difference in size can always happen. Do not try to just exactly say that it is sum of this plus symbol table size will be equal to that. Even that is not going to be true. But yes, there will be a symbol table to match basically.
Also, I would not say it is not exactly like the symbol table followed by Q.O followed by stack.O. That is not necessarily the case.
Exactly.
Okay. The format of .A may be slightly different from .O. All these intricate details I do not know. But the symbol table is there, and this is one of the reasons which increases the size slightly.
Sir, what do you mean by the symbol table?
Yeah, it's you can say it something like that. It gives you a header which says that this defines this function and it is defined at this location of this library. This function, this function, this function. For this function, go to this portion of the library. For this function, you go to this portion of the library. Something like that.
Sir, to keep a record of everything.
Yes.
Not just to keep a record of everything. Think of there's a code out there. This is no longer source code. Okay. So then if you want to link and you have a call to printf or square root, okay, you have to figure out where the square root code starts because there are so many other codes out there. The symbol table kind of does that thing. It says square root, go to line number this, that's where the code starts. Kind of that. Okay. But again, I would say at the beginning, do not try to go too much into what is the format of the library, what does it contain, and so on. I know you're all very bright boys and girls, will get these questions, but first just know how to use them. That's the primary purpose of this starting new off basically. Once you know how to use them, then you start thinking, so what is the dynamics inside? Some of them we'll cover later on, some of them we may not cover in this course. Okay. Because more we try to explain this in this manner, it seems like it's such a simple thing like put a symbol table, put some code, just put some pointers and it works like that. There are lots of other issues that we are not going into and we will not go into this course.
And I think this course is well beyond the scope. You will start understanding certain things when you write compilers. Okay.
Yes, sir.
Okay. Okay. So, for example, I can figure out what things are defined and what are not defined, undefined, using that nm utility. So stack.o use this many functions, of which push, print, stack, pop, these things are defined, whereas these things are undefined. Likewise, it also consists of contains a q.o part, which defines certain things and does not define some other things. Okay. Anyway, so you can look at all these functions that are used, defined with or without definition, using this them mangler utility. Anyway, then this is one part of the thing. You compile and generate this library, but any application like this should know the exact definitions of stack, queue, nodes, node pointers, and all that stuff. So my libstack.a is a precompiled thing. Okay. But if I want to use these functions, I should know what is the input-output behavior of the functions. So these are written in defs.h, stack.h, and q.h. No, not the stack.h, stack.h and q.h. Okay. So even after compilation, the roles of these header files are not vanished. Okay, they are still there. Okay, so you have to somehow first of all, you have to include these files, defs.h, stack.h, q.h. Otherwise, your code will not compile. Because, for example, your compiler doesn't know what a note P is, note pointer is, what a Q is. Okay. So the roles of these header files are not yet finished. Every application program should include these definitions. Function prototypes, data type declarations, and if any, I would say, has defined macros are there. Okay. But then, even after header files, when you want to compile, now what are you doing? GCC -w all stackcheck.c. Since you have included these files, the compiler knows what is a note pointer, what is a stack, what is a queue. But if you straight away compile it, it cannot see any definition of push, print stack, destroy stack, init queue, enqueue, print queue, destroy queue, these things. Okay, because they are only defined or declared as a prototype in these H files. Their actual implementations are present in the library or in the C file. Okay. But after this compilation of your C files to your the form of this library, these .c files are no longer needed, stack.cq.c, because they are compiled and stored here. Okay. So somehow you have to tell the compiler that I have a static archive where you can find the actual definitions, actual implementations of these functions. Okay. So these can be done as you have done in as -lm. Okay. So this is the thing you need to additionally pass during compilation time. So it says that compile this. Those header files will give you the definitions, function prototypes and all that stuff. But the actual implementations will be in a file called libstack.a. Okay, if it is a static library. Okay. But still there is a problem. You cannot do it. Okay. The reason is that this LD does not look into the current directory for searching libraries. Okay. In fact, it has a predefined collection of default directories where, okay, so it has a predetermined list of default directories where it actually searches for libraries. And the current directory dot is not a part of that search path. Okay. But if you compile with the -l flag followed by the directory where your libstack.a exists, with or without a space between this -l and the directory name, then the so-called loader LD additionally search for the extra directories that you provide. Okay. And if it finds that something like libstack.a there, it can now prepare an a.out with these definitions or implementations of the functions being found here and just included in your a.out, in your a.out. Okay, minus capital L adds directories to the default library path. Okay. Any question at this point? How to automate this process, right? I will tell. Any other question? Yeah.
Sir, but this addition is not permanent, right? Like next time also we have to
Yeah,
write
yeah,
this
yeah.
kind
I
of
told you the next question, how to make it permanent. Any other question? I will come to it. Yeah.
So the stack library that we have created, it's in the same directory, right? In which the stackcheck.c program is
Yeah, you
present.
created here locally.
Okay, sir. Okay.
Okay, so how to make it permanent? So that is the next question. So there are two solutions. First of all, as I mentioned, there is how to avoid this minus L, or in other words, how to make it permanent. And also there is another important thing. You do not need to include minus capital L option when you link with the math library, right? So why this preferential treatment for the math library? Okay, the answer is this. Because the math library resides in a standard library directory. And what is a set or list of standard library directories? This varies from machine to machine, from, I would say, different distributions, from one distribution to another of even Linux. Okay. So these are some, I would say, standard directories. Okay. Something like user lib, user local lib. And I think these were more standard, but currently what I have seen that in current Ubuntu machines, this kind of directory is also in the list of default directories. Okay, so if your libstack.a resides in any of these directories, then you do not require that -L option. Okay, then LD knows where to search without any special directive. It will find that library there. It will do the linking. Okay. So all the thing you have to do is to copy your libstack.a to one of these directories. Okay, whatever is considered as one of the default search directories. But if you work as a user, standard user, you usually do not have write permissions to these directories. Okay, so you have to do it. Okay, so if you copy this to any of the standard libraries, I exactly do not know whether this is a complete list of the standard libraries, standard library paths. There may be more. User local lib is there, definitely. User lib should also be there. Anyway, there may be some more directories, but these are essentially systems area. So if you can copy libstack.a to here or here or here or whatever else, then you do not need -L, this flag. And your application program may be anywhere. Okay. But this needs super user privilege because you are writing to a system directory. Okay. So now in Linux, this can be done this way. Maybe in a later class, we'll tell what this sudo does. This is an abbreviation of as a super user do. What to do? Copy this to user local lib, this directory. Okay. Now, whenever you say this, it will ask for your password. Okay, your password actually, not the super user password. So there are two ways of doing it. One is by su, be a super user, or as a super user, do. It requires your password, not the super user password. Okay. Now there are, I would say, plus minus for both this su kind of thing or sudo kind of thing. Ubuntu promotes this sudo. Okay. And then you create this. You just make a copy to the standard library. Now, even if you delete this file from your current directory and simply compile with -L stack without any -L, then compilation succeeds or linking succeeds, and you eventually get that error.out file. Okay, so this is one way of avoiding that -L flag and making it permanent. Okay, but the question is that what if you do not have super user access? Okay, then there is also a way to make it Okay, so library path is not for static libraries, I believe. Okay, I think this is fine. Static library path is for runtime addition. Yeah, oh, no, this is not applicable here. Yeah, okay, fine. So this is how you can make it permanent. Okay. Also, this is, although this thing resides in a standard search path, you still require the header files. Okay, and they should somewhere be there. Okay, and again, as I have mentioned in the last class, the header files may reside in a default directory. And again, if that is the case, then you do not need that -i flag, and you can simply hash include like this. So this is how, yeah, the application programs do not need to know where the header files are, And again, there are standard header directories like user include, user local include. Okay. So a user with super user privileges can copy the header files to one of these directories, and then you can simply hash include like math.h, you can call this. And using subdirectories is also often a good option, because today you are like writing a, I would say, library which has a header file defs.h. Tomorrow you may be writing another library which does not deal with stack or queue, but it may deal with something like priority queues, binary search trees, and that also requires a defs.h file. So if you copy both the defs.h file in, let's say, user include, then the previous copy will be overwritten, right? That's not what you want. And there may already be some defs.h file somebody else wrote. Okay. So what should you do? Just create a subdirectory here, and with the name of your directory, of your library, and put the defs.h there. And now, even if you have two different defs.h into different subdirectories, they can be accessed differently. For example, I can do something like this. So I can write a wrapper. So it says in that include directory, you create a subdirectory with this name. Under this subdirectory, you include this file. So if you now have a binary search tree library, so you can now hash include bst by defs.h. So these two are different files. Okay. And in that case, you have to run sudo make directory user include stack. You copy these things to that subdirectory and simply copy the outer wrapper to user include. And I assume that later you will not build a library with the same name. Okay, so one question is, now you are not seeing that this is not asking for your password. Why? Because for some time, once you are authenticated as a super user, Ubuntu will no longer ask for super user passwords, provided you are working in the same terminal. Okay, for some time, maybe 10 minutes, 15 minutes, something like that. And once that time period is over, it will once again ask for the super user password. So for every sudo command, I do not need to supply my password. Okay, this is a kind of convenience. And then you simply hash include stack.h, which in turn will hash include stack this directory / definitions.h stack.h q.h. Okay. So this is how this works. You can have standard header files in a subdirectory of any standard include path. Okay. Okay, I think this is just how to do it.
Sir?
Yeah.
Sir, when we are writing hash include stack.h, we are not creating stack.h, right? We are just creating, means we are adding in the directory defs.h, stack.h, and q.h. So this staqe.h, like that file isn't present. So how can we include it?
It is present in user include, right? And this is the standard, I would say, default include directory. User include.
Oh, you are including. Okay, I see now. Yes.
Okay. So if I say stack.h, this contains these 3 lines. So in turn, it will include these 3 files in the subdirectory user include / stack. Okay.
Yes,
Clear?
sir. Like all 3 files in one file. Is it like that?
What?
Like stack q1, which is staque, that will contain all 3 files together.
It will not contain. It will contain directives. Include this, and include this. So recursively, this will be included. And if there are further hash includes there, those things will be included.
Those are the exact 3 lines that will be there in stack.h. That sorry, staque.h. So when you include staque.h, its effect will be to first include staque/gets.h, staque/stack.h, staque.h, one after the other.
Okay, sir. Got it, sir.
Okay. Of course, you can selectively, if you run only the stack utilities, you are not interested in queues. You can only include this and this in your source code. Okay. Yeah. Okay. There are too many details anyway, since it is there. So a header file. This is, for example, if I look at the enqueue function. Okay, it takes a queue and an integer to insert in it, and it will return the updated queue after inserting the second argument, whatever integer you specify in the existing queue. Okay. So I think this extern declaration is not needed, but your header file queue.h, this prototype declaration may start with extern something like this. This will give the compiler an indication that this is not defined in your source code. It is an external function. Okay, it can be linked from other libraries, which is external to your program. Okay, but anyway, I think even without this extern, it works perfectly. It is more or less I would say, a legacy keyword. Not sure of any specific situation where this extern is a must. I don't know.
Sir, what is legacy keyword?
That means people have been doing this for ages. Maybe at some point of time this was needed.
Okay.
And maybe needed today also, depending upon your distribution, your exact compiler, exact all that stuff. So it's preferable to have extern. Let us have it, no problem. Indicating that these are external functions. They will not be found in your source code. It has to be linked from somewhere else, either during the linking stage or during runtime. Okay. That's a good idea to define the prototypes with the extern keyword. Okay. Okay, so that's how you can manage, build static libraries. Now we will go to shared libraries. If there is any question, let me know.
Sir, if we want to have a static library, isn't it better to just hash include instead of linking it during runtime?
Hash include will do, if you hash include .h files only, okay. Then this .h file, look at this .h file. It does not implement enqueue. Okay, and it's a bad practice to hash include a .c file. Okay. Again, you're thinking of only small codes. If you think of a big math library having, say, let's say 100, 200 functions, maybe thousands of functions, why do you want to compile every such function when with, I mean, your source code? So they are already precompiled. If it takes 2 minutes time, they are precompiled, they are already stored. You simply link to them. No need to compile every time your source code is compiled. Right. Moreover, every time you want to use sqrt function, there is pointless to say that you will have an access to the source code where sqrt is defined. It's not needed, right? It's too inconvenient. You have these header files, sqrt, abs, pow, everything is precompiled. So precompilation time is saved. It is stored somewhere. And you simply call them. You should know how to call. That's all. Makes sense?
Yes, sir.
Okay, good. You do not need that square root.c or whatever file. Why do you need that? Okay, so shall I start shared libraries? Okay, maybe I will. So basically it's exactly the same. Only thing I have to change the compile time options little bit, and also the archiving command that generates the final shared object. So once again, I assume that I have this header files and these source files, and I want to build the library called libstack.so. Instead of A, it will be shared object, SO. Okay, it's a dynamically linked library. In Windows, it's called DLL, dynamically linked library. Once again, the first step is compile individual source file with -c option to generate the object files. But this alone will not suffice. You have to compile each of these individual source files with an additional flag -f pick, where pick stands for position independent code. Okay. So in a sense, this pick is needed for because the objects in that I would say the functions or defined functions in the object files may be later relocated anywhere. Okay. And therefore, you should not, in a sense, I would say, you always say that my sqrt function will start from here. Okay. So pick essentially does like that. Okay. Position independent codes. Okay. And then instead of calling AR command, you call GCC -shared. Okay. Compile this with the -shared flag. That will create this static object file, shared object file. Okay. So the extra thing you have to do is you have to specify this -fpick flag and archive this using GCC instead of AR, but with the -shared flag. That will create the desired shared object file. Okay. Yes or no?
Sir, please explain FPIC.
Yes, you don't have to understand to, I would say, to.
No, I meant what is this position independent? I don't understand.
The point is that this may be this objects stack.o, q.o, they are relocated. Okay. Somewhere. Okay. And something like one possible example is something like this. Instead of just saying that, go to this address. Okay. So this is the hardware address, like maybe go to the 15th byte. Okay. So this is position dependent. Whereas position independent means go 15 points ahead. So wherever you are. Okay. So that's the kind of thing. Irrespective of wherever you are, if I want to tell you go to the address 15, then this is a fixed address. It's a position dependent. On the other hand, if I say just move 15 bytes ahead, this is position independent. So from wherever you are, you can move 15 bytes ahead. This is the kind of thing that if this pick thing generates, and that is needed for, I would say, the shared libraries. Okay. Again, I would
Yes,
say,
sir.
okay, you do not have to understand with the full implementational details what is meant by this, because this requires you to look into the assembly code and all that stuff, which is very difficult for you to follow at this stage. Okay. Okay. So this is how you generate this as a file. Fairly straightforward. But then how to include it. Okay. And of course, like that nm, you can just find, you can run this nm on this to find all the defined and undefined symbols. I am not showing you the results. Now the next question is how to link libstack.so. But link is, I have quoted it in italics in the sense that shared objects are not meant for linking in the linking stage of your compilation process. Okay. They are linked to your executable during runtime. Okay. So linker is not supposed to link the stack and queue functions to applications. These functions will be read from this during runtime. Okay, so that's the difference between static and shared libraries. Okay. Again, you need that -l option to add the path of the library. So, for example, you can do it like this. As a super user, copy this to user local lib, then you compile. Okay. With -l stack, it will generate error out. Exactly as you have done for shared static libraries. Okay. And in fact, if both the static library and the shared library is present in your machine, its behavior I am not sure, but in my machine what happens, this is Ubuntu 20.04. It uses the shared library. It ignores the static library. Okay. Maybe to generate smaller codes or whatever. That's the policy of my machine.
By default, it will take the dynamic library.
Oh, that
Linux it always takes by default.
By default. Okay, but I do not know whether it's a Unix specification. I do not know.
Yeah, no, I don't know all that also. Linux does.
Linux does it, yeah. In my machine, I have checked it. Yeah. Okay. So you can see that this is a dynamically linked file by using nm, name mangler. And you can see in your a.out, destroy queue, destroy stack, enqueue, init queue, init stack, they are not defined. U is undefined, undefined. Okay. Similar to rand, putchar, okay, exit. Okay. So now we can see that these functions are no longer defined in your a.out. This will be linked during runtime. Okay. So it actually produces a huge output. I have filtered it through this grep. We will study grep later. Only those undefined things. So it's something like this. Okay. Okay. So the intentions are satisfied. I have a shared library. This is not linked to your a.out. As you can see, using this nm utility. But the problem is that you can still, I would say, perhaps not run your a.out. Despite that, you have copied that user local lib. Okay. I do not know. I didn't experiment with this. If I copied that to this directory, lib x86 or x86 under 64 Linux GNU, possibly it would have worked. I am not very much sure. I have not done it actually, or in /lib64. So the problem is, once again, it is the same. User local lib is not part of the default set of paths from where your runtime loader will, I would say, load shared libraries. During compilation, this is fine. You do not need that -l dot flag because, okay, l dot or l, this flag, l, this directory -L, because the compiler knows this, because user local lib is a I would say one of the standard library paths. So compiler knows. It knows what things are defined there and all that stuff. Okay. Unfortunately, the runtime system does not know. And therefore, if you run LDD, you will see that it requires this shared object. It knows where to find. It also requires this runtime library, which has this push, putchar, and exit, things like that. They are also undefined, but they can be found in this file. Okay. This is also needed for some reason. I am exactly not sure which one includes what, but it says that this is not found. The compiler found it, but the runtime system did not find it. Okay, so somehow you have to tell it that you search user local lib, you will find the definition of or the existence of the presence of libstack.so in that directory. So how to do it? So once again, there is an environment variable called ld_library_path. You need to set it. Okay. So if you, for example, use the Bourne shell, just for the moment, without understanding much, this can be done. You set the LD library path and export it. And if you use another shell, the command is essentially that's the same thing, but in a different way. Okay. Once you do this, then if you just say LDDA.out, this is now added to your default library path, runtime library path. Now you run LDDA.out, you can now see that this is found here. Okay. So now you run, no complaints. It will load the enqueue, dequeue, init queue, push, pop, all the things in runtime from this file, and you are done. Actually, there is a compilation time flag. It's a very peculiar looking flag, which you can give during this. This is the -w all, and there is something minus again. I think it is a -w thing. It's a very funny looking flag, so that your code itself stores the thing there, and you do not require that -l. I mean this. You do not have to set this ld_library_path. Okay. Anyway, anything else? Okay. So let's see. Is it clear up to this point?
Sir, one question.
Yeah.
Suppose I do not want to change the environment variable. So what are the options do I have while running the? So one of them is that funny looking flag you told, and the other one.
Other
And
one, I didn't actually
is
try.
there any other?
For example, this leaf slash x86 underscore 64 Linux GNU is possibly a default library path. So if I copy libstack.so there, then also it might work. But frankly speaking, I didn't try it out. Okay.
Okay.
Okay. I didn't try. You may actually try and tell me what happens.
So like the only option for now is to just set the environment variable.
Yeah.
No, so here the -L flag will still work, right?
For compilation, not for runtime.
Compilation, not run.
Compilation work.
See, runtime, you have to, there can be so many directories, subdirectories. So you have to tell the system where all to look for things that the system is looking for. And the environment variable or the default thing is the way to do it. So either you copy to the default or you set the environment variable. I don't know
So
of any
like,
third way.
if I store the file in the current directory itself, will it not look for it there?
No.
So that no. See, that's why if you run in Linux, okay, you run your a.out, do this, okay, just compile a simple C file in its standard Linux, okay, and just run a.out. A.out is created in your present directory, right? It'll give you an error. It says cannot find the file. You say /a.out,
Yeah.
it'll run it. Okay. So somehow dot is not looked at, basically.
Okay.
By default, it is not looked at. And basically, it does not look at anything other than that you set in the path or these default ones which are very sure. I'm just guessing. One of the reason is, see, for example, you want to do, some standard Linux command. Okay. Linux commands are, there are two types. There's a built-in things which are not exe files, not executable, and there are executable files. So if you do that and by mistake, if you have named one of your executable files in your current directory like that, it's going to execute that. If you had dot as something that default that the system looks at. Am I getting through?
Yes,
See,
sir.
think of ls. Okay.
Yeah.
If you name one of your commands, output files ls, and then run. Suppose it allows you to run just ls and by default pick up things from your current directory if it is there. Okay. Then you run your ls. But then you actually wanted to do ls of the system, maybe. So it does not know which one do you want. So it says whatever you want, you tell me explicitly. Either you give me the full path to run it, or you set the path variable to say that, okay, it's safe to search in the dot directory also, or whatever else directory you want me to search. Does that make sense?
Yes, I understood.
Okay, so I think I need a little break. So maybe 5 minutes break. We will restart. Maybe another half an hour or so I will continue. So let us have a 5 minutes break. Okay. Yeah, I am back again. Okay, so let us quickly finish the remaining part of this set of slides. Actually, two things I do want to, or we do want to cover, I would say. First one is some useful GCC options. So that -w flag is actually more, I would say, complicated than you see, than you feel it is. As -w all has nothing to do with wall. It's not a Facebook wall. Okay. It tells the compiler that during compile time, it generates many warning messages, but not all. Okay, I'll switch to presentation mode. Maybe easier for you to see. Okay. And this includes several things which you can individually call. For example, -w comment, warn about nested comments, the -w format, warn about type mismatches in scanf and printf, w unused, warn about unused variables, -w implicit, warn about functions used before declaration, all that stuff. Okay. So you can individually call these things, and sometimes some of these things have even subcategories. Okay. Yeah. Return type. Warn about returning void for functions with non-void return value. So you're supposed to return something, but you are returning nothing. Okay. So that kind of warning messages. And as I mentioned, some of this may have subcategories. But this all is actually not all. It does not include, for example, these two things. Warn about implicit type conversions. Okay. For example, if you just pass one integer to let's say square root, there is an implicit type conversion of that int to double. And without this, I would say, compilation directive, you cannot see that compiler is doing that automatically for you. Warn about shadowed variables. There are many other things. So you may look at these things, or you should look at these things in the reference that is provided. And this is something quite serious. Convert warnings to errors. Okay. Anyway, so this is something about this -w. We will use the next two flags, -g. So add debugging information in the executable and object files. This will be needed when you study the GDB debugger. And you compile with -pg. This will be needed for the profiler called gprof. Okay. And there are a lot of things about the optimization. The default behavior is do not optimize. And O1, O2, O3, there are different levels of optimization, but you will not understand these different levels, how one is different from another. Now, the point is that if you set these optimization flags, this gives additional burden to the compiler, optimize the code. Okay, and that takes time. So when you compile something like assignment 1.c or small programs, it doesn't matter. Okay. And you may always use -O2, for example, because they generate more efficient codes, efficient in terms of running time. Okay. But if you are compiling huge, huge source files, okay, this optimization may, for example, increase the compilation time quite considerably. Okay, for assignment 1.c, it perhaps doesn't matter. Okay, because it's simply few hundred lines of code, or maybe 1,000 lines of code. Doesn't matter. Okay, But if you are, for example, compiling a source code for a kernel, okay, then optimization may take too much time. Okay, so during debugging, it's preferable that you do not include any optimization flag. Okay, but in the final product, you use this because it will be more efficient. And in the final stage, possibly you will spend that time, extra time. Okay, maybe 1 hour for compilation, it's okay. But if you avoid this during debugging, maybe you can save a good amount of time. Okay, but anyway, what these optimization levels do exactly at this stage you will not understand. Okay, I hope in your compiler course you yourself will have some experience, will gain some experience. So what different levels of optimization mean, and how your code can, how your compiler can do it. Anyway, and this is a verbose mode, print help messages.
Can I interrupt for a second?
Yeah, do please.
So the other thing for this course, do not use the optimization thing unless you're very sure of it. So what the other thing that it messes up, when we do the GDB debugger after this, you will see there are function call stacks and things like that. So you'll get a trace of which function called which function called which function, what are the parameters and so on. Now, again, we cannot explain to you right now until you have done some level of architecture at least. Okay, but when you compile with the optimization flags, okay, some of those debug informations will get completely messed up. So you may think that a parameter has value 37, okay, but then actually the parameter has value something else. Don't ask me why right now, okay? Until you know about registers and register optimizations and all, you will not understand this.
It was some like they may even be lost.
Right. So when you, in this class, do not use the optimization flags, because then if you do that and then you try to run with GDB and all, and you try to debug with that information, okay? So when you debug, you do not have the optimizations on. As Eddie said, during development stage, you are debugging again and again, making mistakes, correcting things and so on. Do not use the optimization flags, okay? Because then it will be, first of all, as Eddie said, that time-consuming compilation for large codes, and your debug information, the debug help that you get from the debugger gets messed up at places. It is only after you are absolutely sure that the code is correct. Now it can go to your customer. Then you compile with the optimization, because then you can afford to spend that little bit of, or whatever, not little necessarily, large bit of extra time also, because you're going to compile only once. And then it's going to be used by, thousands of your customers maybe. So it's more important that their code runs faster rather than you spend compiling it once, large amount of time. But do not use it in this course. You can just play around with it, but then debugger plus optimization will mess up your life. Okay. Eddie, I'm done. Thank you.
Yeah. Okay, so if you look at the man page for GCC, you will see there are hundreds, even thousands of options. And I would suggest that the set of options that you have already seen is already a good thing, a good compilation to start with. All the different things, all these -w things, -f things. This is a huge compilation of, I would say, options that the compiler supports. If you look at the man page, you can see it. But I think for the moment, it's sufficient that you have some confidence in using the options that we have already seen. We do not need anything beyond this list in this course. Okay, possibly. And if you need something very specific during some specific chapters or sections, we will tell you. Okay. Okay, so this is the last.
Sir, what was profiling?
We'll see later. Please wait. Okay. Within a month we will.
Yeah, we'll teach you that. We'll teach you that.
Okay, so this is the final bullet of today's, I would say, somewhat long introduction to GCC. So the C preprocessor. Okay, so you know that it can be called by CPP. Okay, and it has two basic jobs. First, all files that you want to hash include, those files will be simply inserted in your code by the C preprocessor. And second thing, it will make literal substitution of the macros. Okay. Okay, so I think hash includes are something you have already seen enough examples of. Now we will talk a little bit about the macros. Okay, so they can be defined and used in two ways. Okay, first of all, you use hash defined in your code. Possibly you have done in your CE, your PDS course or algo course. And second thing is that you can also define things, use the command line option -d when you compile. Okay, so one by one we will see how you can do these two things. And we will use macros in two different ways. First as flags and second as values or expressions. Okay, that can be substituted. Okay. And there is another thing, macros can be parameterized, but we will not study parameterized macros in this setup slides at least. Okay, this is a complicated thing. Anyway, so first let us look at our first use of macros as flags. So if you want to do it in your code itself, you just say hash defined macro name followed by nothing. You are essentially defining a macro called macro name. Okay. It is to be used as a flag, whether it is defined or not. Okay, so that's the idea. In fact, whenever you define something this way, it gets the value 1. Okay, anyway, that's okay. You can undefine, something was defined, you want to undefine it, so use this hash undef macro name. And this is a conditional check. If macro name is defined, then do something. Or another thing, if the macro name is not defined, if not def, then do something. And there is something called hash else. So if it is defined, do something else, do something else. Okay. I will soon give you an example how I can use these things. And whenever you open some if thing with or without else, it should end with this special preprocessor directive endif. So your if is ending. Okay. Okay, so now let us look at it. An example. It's a synthetic example, but it illustrates what you can do with those primitives. So you define a flag in your code and let us give it the name myFlag. Okay. Now inside your code, you say if this is defined, then print myFlag is defined and you undefine it. Otherwise, you say myFlag is not defined. And if. So this is the if def, else it should end with end if. Okay. And after coming out of this, you are telling if it is not defined, which should be the case. Okay. Then you simply print this is undefined here. Otherwise, say it is still defined here. Okay. So now if I compile this and I run it, I will see because it is defined. So I will see this. This is defined. And after this, before this end if I am also undefining this. So now this condition is true. So I will see my flag is undefined here. This is precisely what happens. Okay. Now what you do, if you simply delete this line from your macros.c and now compile this, then this is no longer defined. So this condition is no longer true. So this else thing will be in action. So it will say my flag is not defined here. And inside this else block anyway, you are not defining. So here also it is not defined. So this thing will be executed. My flag is still oh, sorry. It's not defined. So this will be executed. Okay. Now, what happens when the CPU processor handles this if def, if not def, else, these things? Okay. The idea is that if it is this code, the preprocessor knows that a flag or a macro with the name my flag is defined. Okay. So what it will do, it will keep this printf in your code. This L part will simply vanish from your code after preprocessing. Okay. Also, what will happen? For the moment, it undefines this flag. And when it comes here, the preprocessor sees that it is not undefined. So we will keep this line and it will simply throw away this line from your code. Don't worry, your C program will not change. But whatever that CPP does, it generates that .i file. Okay. In the .i file, this line and this line will be absent, completely absent. So this is not something like a standard if something, then do this, else do this. This is not a C code. This is a preprocessor directive. Your preprocessor will keep this line and simply throw away this line and this line from the partially digested code. Is that clear?
Sir, whatever we have written under if def means whatever, there is nothing like only the next line, like one line will be under if. So means undef my flag isn't like it doesn't seem to be under if of this.
Yeah, no. If def must end with endif. Possibly there is an else block. Okay. But the point is that unless you say endif, the definition of this if def or if not def is complete. So whatever follows, this is all part of this if def or its else block. Does that answer your query?
Yes, sir.
Okay, this is kind of opening bracket, closing bracket. Okay, but this is done in a different way. Okay, so that is the reason you need this endif. Otherwise, the preprocessor does not know up to which point the scope of this if def is extending to. Okay. And suppose now I have what is that called? I have deleted this line from macros.c. Then if I run it, what the preprocessor will do, it will see that this will not defined. So it will go to this else thing. So what it will do, it will simply remove this part from your code. It will include, it will have only this in your code. Okay. And then once again it comes here, it sees that it is not defined. So it will only have this line in your code, throw away this line from your code. Okay, I will show you an example. This example itself in the next slide, I believe. Okay. So this is another way. We can also define the macro in your during compilation time. So you do not have this line here, has defined my flag here, but you are defining it here. This is C minus W all minus define my flag. Then you say macros.c. Then this is equivalent to putting something like has defined my flag here. Okay. And then if you run, you will see my flag is defined and my flag is undefined. And if you run only the C++, C preprocessor on this and see what happens, you will see this printf statement is there. This printf statement is there. This has vanished from your code. This has vanished from your code. Okay. Understood?
Sir, can we use also -L to get the preprocessor file?
-L.
I mean capital L.
Is the library path. No linking, no actual compilation is done by the C preprocessor. It only literally introduces your hash included files inserted in your code, plus it will process macros. At this point of time, there is no effort of compilation, generate any kind of system level code. And the linking and all the stuff, those things will come even later. -L is not, I think, not at all applicable here. Why do you ask this question? I do not really understand.
Sir, sir, why have you written macros.c after d my flag?
Some C file I have to tell, right? The C file has the name macros.c.
Oh, okay, sir.
Yeah. So I think I have, yeah, this is the file macros.c.
Sir,
Yeah. Any other question?
Sir, I meant minus capital E. Sorry, I said -L.
Capital
E.
E. What does it do?
Sir, I think means it should get, means if I run it, I should get the preprocessor file outputted on the terminal.
Yeah, it shows you the output of the preprocessor, but how does that help you?
CPP does the same thing, right? Maybe GCC minus capital E only invokes the CPP and generates this output. I never tried this minus capital E flag.
But what is your question here? Are you asking, we're just trying to understand, are you asking that use of -E, or can you please restate your question?
Means sir, how does these two things give the similar, like just like, I mean,
no, see, GCC anyway calls CPP. Okay. Because so CPP is just one step. Before the actual compilation, it just preprocesses the file. What is preprocessing? Use the hash includes, do macros. There's some others, but we'll not go into that at all. Okay. So output of the CPP is also a C file. But now there is no dependency on .h or anything. There is no hash includes or anything you will see. Okay. This is what you are seeing here. -C will also show you that because it's calling the same thing underneath. Is that clearer?
Yes, I got it.
Okay. Okay.
Okay. So any other questions on this? No, okay. Then let me tell you why defining a macro during compilation time is good and why it is bad. Okay, so why it is good first, good things first. So defining macros using -D instead of hash defined hardwired in your C source file gives you more flexibility. During the compilation time, you may define it or leave it out. Okay. Why this is needed? For example, look at this. So you are writing your assignments and you define a flag called diagnostic that will print many diagnostic messages. like intermediate values and all that stuff. And this will be needed for your debugging purpose. But when we or the TAs check the assignment, we are not interested about your diagnostic messages because that will clutter the screen and your actual output may be lost inside those. Okay. So your TAs will compile without this flag. Okay. Your TA does not require these diagnostic messages and compiles without this flag. Okay. So this gives you an indication how this -d flag or defining or leaving undefined macros gives you some compilation time flexibility. Okay. So this is the good thing. A bad thing that we will see in an example soon is that sometimes programs may refuse to compile when macros are not appropriately defined. Okay, we will see an example soon. Okay, so again, what is there? Anyway, so okay. There is another utility of using these macros as flags. First of all, as you see, diagnostic things like that, they may be helpful during development. And also, it may protect some parts of your code. Okay, for example, think about that stack.h file. Okay. Or for that matter, stdio.h, math.h. What happens if you include a header file twice? Okay, accidentally or even unknowingly, knowingly or unknowingly, what will happen? Now, if these two things are, I would say, defined twice, the compiler will say that node P, okay, a stack is defined twice. These two definitions are basically the same, but it will complain that this is defined twice. Okay, and compiler will refuse to work further. Okay. You want to define stack, do it once and only once. Not more than once, not less than once, exactly once. And this is how, using macros as flags, this can be guaranteed. So essentially this flag, okay, will prevent this portion of the code or the header file from being included multiple times. If it is not defined, include this and also define this. So later, whenever again you want to include stack.h, it will see that this is no longer true. So it will simply skip this part, go to endif part. Okay, so this will prevent the same header file from being included multiple times accidentally or intentionally, if you protect it this way. So if you look at the standard C header files, you will see this kind of things. If not defined, something __math_h, something like that, then define it, do all the things, in the end you have endif. So that you cannot accidentally or intentionally or unintentionally include math.h twice. That will be problematic for compilers. Clear? This use?
Yes, sir.
Yes, sir.
Good. Yes. So good. Okay. Second, I can also use macros as values, but not values for immediate evaluation, but for substitution. So let's say I have defined two macros. Expression 1 stands for 100. Expressions 2 stands for 10*10. Okay. Then I can write this code. If expression 1 is equal to expression 2, printf this is equal to, otherwise printf they are not equal to. And then I look at whether expression 1 is equal to expression 3. Then I say this thing, and expression 4, something about expression 4, I will say is equal to. But you see that in this function, expression 3 and expression 4 are not defined. Okay, therefore, if you want to compile this program, it will refuse to compile because expression 3, no macro of that name is defined, no variable of that name is defined, nothing. There is no way the compiler knows what you are essentially talking about whenever you talk about expression 3 or expression 4. Okay. So this program cannot compile because expression 3 and expression 4 are not defined, but you can define them during compilation. For example, you can do something like this. Expression 3 you define as 50 plus 50. Expression 4 you define as 5 plus 5. Okay. There you give the file name. Now this compilation is successful because the compiler knows, or the preprocessor knows, how to substitute something for expression 3 and how to substitute something for expression 4. So 50 plus 50, it is 100, right? What was expression 1? Let us see. Expression was 100. And I am comparing expression 1 with expression 2. Of course, this is also 100. Expression was expression 3. What is expression 3? 50 plus 50, I defined that way. So 100 is equal to 100, so it will print. Now you will see something peculiar. Expression 4 should evaluate to 10. Okay. And I am comparing expression 100 with 10 star 10. 10 star 10, right? So that should be equal, right? But it says expression is not equal to expression 4 star expression 4. Can you tell me why?
Sir, we discussed that in the first class, that thing. It would evaluate 5 into 5 and those the rest of the 5s it will add.
It gives 35 as value.
Sir, it won't follow that bracket thing. It would just 5 into 5 and plus 5 plus 5.
Okay, so it will be which first class? Is it a PDS?
So it was in software engineering.
Okay, software engineering. Okay, because I do not think we have covered in this PDS.
Yes, sir, my bad. It was in other class.
Okay, some other class. Okay, so macros are literally substituted. Okay, not evaluated before substitution. So literal substitution of expression 4 star expression 4 essentially means if I use the C preprocessor, I will see 5 plus 5 star 5 plus 5 without any parentheses. Okay, so that's the difference between variables or function calls and macros. They are meant for literal substitution, not evaluation then substitution. Okay, so be careful about this. Okay, so this evaluates to 35, not 100, and that's why it is saying, yeah, no, not equal. And I think there is just one more thing. I suggest that I leave it to you. How to quote strings with spaces, perhaps. Okay. How to use, strings with spaces or something like that here. Okay. So I think I stop here. You need to quote. Okay. You read it. You should be able to understand because you now know what literal substitution means. Okay. Okay, so one thing that we are not going to cover is how you can pass. So if you say /a.out 1, 2, 3, some command line arguments you provide, how your main function can access that. So this is argument count, and this is the array of strings, argument values, and how you can convert these strings to integers, floating point numbers, and so on. And this is another important thing. Main always has the return type int. Never it is void. Okay, whatever is written in certain books, it is always int. And this int will actually go to the so-called shell. How the shell can get this value and what it will infer from that value. These things are for the moment, I would say, a little bit too advanced. But we will use from time to time some examples where we send command line arguments and you can access this from this, I would say, character, an array of strings. Okay, so you read how we can do it. Okay. Okay, so it's not exactly a GCC feature, it's basically a C feature. It has nothing to do with GCC. Okay, so that's why we keep it as an appendix. Okay, I think we stop here. It's already how much time? Yeah, it's already 2 hours of dead. Okay, so let me know if you have any immediate questions. First of all, I will put this entire set of slides in the web page, and I will also, I have already given you reference of some introductory GCC manual or tutorial or whatever you call. I will specify which sections you should carefully look at. Okay. This I will do after the class. Let me know if you have any immediate questions.
Sir, in the previous slide, we had that macro. Yes, sir, this one. So can this work with the single quotes also?
Which one?
Sir, the first line.
Yeah, it should work. There are some subtle differences between these different types of codes, so we'll see later.
Okay, sir.
I think in this example, single quote will be perfectly good. Only backquote is something different. Backward quote. So don't use this in this context. We will see this later when we talk about shell programming and all that stuff. We will see.
So once again, there are no assignments this week. We thought we'll give you some time, but some of you had problems installing Linux and so on. But again, how much you want to learn is up to you. We'll have tests and all later on, but please write programs, small programs, try out the different options. All those warnings, for example, just make small things, create a variable, do not use it. Define a variable, do not use it. See what warnings you get. So just practice a lot of small programs you write. And next week after we do make, which kind of, is the other part of working with multiple files together, then we'll give you some assignments with everything. GCC will have to exercise all this library thing, GCC, make everything together.
Sir, I have one question.
Go ahead. Tell.
Sir, whatever we have learned till now, is this all applicable with C++ also?
Almost all. I would say almost all, yes. Everything applies to G++.
Okay, sir.
Only thing, there are some small things, like instead of C include path, you should say CPP include path or something like that. I exactly do not remember the environment variable name. Otherwise, almost everything without any problem will work for C++ files. Only instead of GCC, you have to call G++.
Yes, sir.
Yes.
So the other thing, in response to your question, as we mentioned in the first class, so one thing is whether the same commands work with C or C++ and C++ or not. But C, whichever language you programming, the first class that we mentioned, that making a habit of doing things properly is very important. And in every language, you will find basically these rules, these different options, okay, different ways, these making libraries, debugging tools, and so on. So kind of whichever language you program in C or C++, whatever, as I said, most of what we're talking about is applicable to C++ also in Linux. So kind of get that thinking process in your mind. This lab is kind of, we started this lab with the idea that we'll put all these ideas together and kind of start you off rather than teach you a lot of things. But
Sir, I have
expose
one
you
more
to lots
question.
of small things. Yes, go ahead, please.
Sir, suppose if later on, if we want to learn some other language and we want to do the same things which we have done in for the C language in those languages. So, what exactly should we search to get
So
this?
see, when you program in that, search for the tools for that, you will see many. See, debugging, for example, will teach you GDB. GDB is a text-based command line debugger. Okay. Now in the real world, you will use actually very sophisticated, user interface based debuggers. Some of them are actually built on GDB. So the idea is basically, so don't worry about how will we find when we learn that other thing. Okay? So for example, when you go and real world and debug, and then see the same kind of question is that how will we find what tools to do, other tools we have for debugging and so on. I think software engineering course, I think they give you a slide where they talk about some of these tools. So you have GDB as well as you have very good graphical user interface tools also. Okay. But short answer to your question, don't worry about it now. Just get into the habit, practice what you have. When you come to the new language, you will find there are communities and all, and you will immediately, as you learn the language, you will find the tools for that also. Anything else?
No, sir, that's fine.
Okay, then if there are no further questions, so Eddie, I think we can close the class.
Yeah, I will close this.
It's a long class.
Yeah, it's already 2 hour plus. So
Have all of you been able to install Linux or somehow get access to Linux? Anyone who has not been?
yeah, that's a big question.
Sir, any version of Linux will do, right?
Yes, yes, for these simple things, almost any standard.
Almost everything will do.
What have you installed? It's Utsav, right?
Yes, Oracle Linux.
Oracle Linux, okay. Make sure you have the GNU utilities, GNU, capital G, small n, small u. Okay. I'll also just send me a mail, I'll also check. I think any Linux will do. They should know utilities, everybody should.
I check it has the GCC and the GDB, but
okay, right. Then gprof and all will be there also. Make is there everywhere.
Okay, sir.
That Valgrind, almost everybody will have to install. It's a one-line thing. Okay, when we teach you Valgrind, we'll let you share on the shell programs and all. These are all part of any standard Linux. You will be fine.
Sir, only a terminal environment will be sufficient for this course. Means not a desktop environment is required.
No, but to write your C files, you can write from the terminal if you know VI or Emacs editors like that. Otherwise, you can write in any text editor. So for all the commands that we will run, the terminal will be fine. But to create the C files or the .h files and so on, there are terminal-based editors if you know them. Otherwise, you can use the standard text editor that comes with. All Linux version will come with the standard text editor. Is that fine?
Okay, sir.
Okay, so silence means I will assume that you have all been able to kind of start off with Linux. So keep on practicing. Next week we'll do make. And then we'll give you assignments. Okay, in that case, thank you. Rohit, let's close, right?
Okay, I have already closed the.
Yeah, screen share. You have stopped it.
Screen share after I have stopped the recording also.